All right, so yesterday we looked at the superpositioning, the adding and subtracting. So let's have a look at multiplying two functions together. So key things to look for is, well, obviously when one function is equal to 0, when you multiply them together you're going to get 0. So that's how you're going to find your x-intercepts. 1 also becomes a key feature, because if you multiply by 1, you're going to get the same value. So knowing where 1 is on these is going to be important. Now, you see the note I put there. So it's an idea to first of all work out where it's going to be positive, where's it going to be negative, and that gives you an idea where the curve's travelling behind. So some other things to keep in mind: discontinuities. So again, they're not going to disappear. So any exclusions in the domain of one of the functions will become a discontinuity in the new function. X-intercept, well, that's what I just mentioned. Is if you've got 0 on one of them, multiply them together, it's got to get 0. Again, we're going to retain some symmetry. Odd times odd, even. Odd times even, odd. Even times even, even. So basically, if it's the same type of function, when you multiply it together, you'll get an even function. Okay, let's have a look at this one. So x squared times x plus 1 times x minus 1 cubed. So I've drawn the three individual graphs there. So what can we tell? Well, they're not asymptotes that I've drawn in, by the way. I'm just dotting them in to say these are going to be boundaries from where it might change from positive to negative and so on. So if I look starting on the left, I can say, well, yeah, the red curve's positive, the blue one's negative, the purple one's negative, positive times negative, positive. Then in between the next two, positive times negative. Then we go positive times negative. Then we go positive. Now, each of these x-intercepts of the individual graphs are going to become x-intercepts of the new graph. So straight away I know that in this section below, that's got to be a turning point there. Because it's going to stay negative, but it's going to touch. Now, of course, we still know our ideas from polynomials in that the root will behave like the power. So we've got all those sorts of things we can use as well. But basically we end up with, can you see it there behind that purple? It's a green graph in there. It looks like, and that's to do with the scale, I guess, it looks like I'm just going flat across here. But I promise you that is turning, going down a little tiny bit, and then coming back up again. Now let's get rid of the purple. So there we see it there. So it is actually inflecting. It's just that the scale is such a small number that it's staying that close to the axis. All right. Division is essentially the same, because division and multiplication are the same thing. It's just you're multiplying by a reciprocal. So you can still use the same sorts of ideas. Difference being, of course, the bottom of the fraction. The x-intercept of the function on the bottom will no longer be an x-intercept, but it'll be an asymptote, because the bottom of the fraction can't equal 0. So do the same sort of idea. Graph function x and g of x separately. So let's say we're going to do this one. X plus 1, x minus 2 over x plus 2, x minus 1. 4 straight lines, basically. There they are. Okay. Bottom of the fraction can't equal 0. That's going to give us our vertical asymptotes. So which ones are on the bottom? We've got y equals x plus 2 and x minus 1. So those red ones are asymptotes. Okay, they are asymptotes. So once again, we'll work out where is it positive, where is it negative. So I've got negative, 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 positive, positive, negative, 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 positive, positive, negative, negative, positive, 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 negative, and positive, 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 positive. So, okay, we know the sections that we're in. Now, we know these ones are asymptotes. The other x-intercepts will still be x-intercepts, so I'll plot that as it. Okay. The y-intercept is always easy to find, and this one turns out to be 1. Okay. Now, what happens out at the extremities. So the sorts of things we're looking for, dominance, horizontal asymptotes, things like that. Well, this one's a polynomial on a polynomial, so I'll do a polynomial division. Well, 1 turns out, you can see there when I do my division. I suppose the other idea I could have used with this one, the top's a quadratic, the bottom's a quadratic, so I could have just done limit as x approaches infinity. That would have found it as well. Okay, so let's draw that in. Red, don't go. And it pretty much has to do that. We know it's got to be in this top left-hand corner. It's trapped there because it can't go through these asymptotes. So it couldn't go in this positive bit because it can't go negative. So it's forced to be in that section. So in fact, pretty much all the way along, it's forced to be there. There's nothing else it could do. So that's pretty much enough information to draw that graph there, the dark blue one. Sine x over x. Okay. There's x. We're going to divide it by sine x. Remember our limit. Okay. Because at the origin here, we've got 0. Well, 0 over 0, that endless problem. So we would ordinarily think, oh, there's a vertical asymptote here, until we remember our special limit. So we know actually it's going to go to 1. We're going to have a point discontinuity at 1. Okay. Whoop. We end up getting something like that. Okay. And if you think about it logically, you're getting a sine curve and you're dividing by x. So you're dividing by bigger and bigger and bigger numbers. So it's still going to wind along the x-axis, but it's just getting smaller and smaller as you go along. And odd divided by odd, so it becomes an even function. So it's reflected on the other side as well. There it is. All right. Just a few to play with.